My name is Wan-Teh Chang. I'm going to talk about the network stack in Chromium. A few minutes ago, I sent the URL for the slides to Chrome team, the Chrome team email alias. So if you have a laptop, you can search for an email from me, and then you can look at the slides. So when a user types in a URL, a universal resource locator, the browser needs to fetch the resource from the network. And the network stack is the component of Chromium that actually goes to the network to do that, and also potentially caches the resource for the next time. It's amazing that in the short history of Chromium, we have already written the network stack twice. Originally, we started using the V9net library, which is really a component of IE. And we did that to get something working very quickly. And also, we believe that after more than 10 years of the web, every OS should have a very good built-in HTTP library. And we believe that should be the case for all the three major platforms. But we run into some problems, so we switched to another library called WinHTTP on Windows. And it works mostly just fine. So that's what, so WinHTTP is actually what's shipping in Chrome 1.0. But gradually we run into some limitations of WinHTTP, and it's very difficult to overcome those without a source code. Just name one example is that you cannot use WinHTTP to download a file larger than 2 gigabytes. And these days, with these DVD-ROM images, there are a lot of downloads that are larger than that. And there is no way for us to overcome that. So in last July, we started to realize that it's really time to write our own network stack. And also, we believe that that will also help the porting efforts to Mac and Linux. So in Chrome 2.0 beta, we are using our own cross-platform network stack. And this also, so one reason what I mentioned earlier is that it allows us to fix bugs easier, but we also have a lot of ideas to improve performance. So this allows us to experiment with those ideas. So in the source code, all of our network stack source code is under a single directory net. And then under that, there are several subdirectories. And most of them have very obvious names, like HTTP. The HTTP subdirectory contains the implementation of the HTTP protocol. And then there's another subdirectory for FTP. And then there is a subdirectory called URL request. And for most of you, that directory is the most important because that's really the rest of Chrome uses the network stack. They issue a URL request. And the URL request will create the appropriate proto handler to handle that URL request. We also have a subdirectory called proxy for the to handle proxy and get a system proxy settings and so on. And then there is a directory called underneath net called base, which contains the basic socket implementation, SSL, certificate handling, and so on. We also have our own test server that is only used during for our unit test. So the network stack is actually something that is possible to use independent of Chromium. It has very little dependency on the rest of Chromium. We only depend on three other components: the base component, the V8 JavaScript interpreter you only use for interpreting the proxy autoconfig files. We also use the Google URL library. And then we use just a few open source libraries to decode HTTP content decoding, such as zlib or gzip. So that's pretty much it. And most of the code is cross-platform. We hide platform dependency in a small number of files. So if you need to port the network stack to a new platform, you just need to provide the OS bindings for TCP sockets, SSL sockets, getting the system process settings, or how to access the system certificate store. That's it. Then if you need to use the network stack, it's useful to know the threading model and the I/O model. The threading model is mostly single-threaded. So we do most of the work on a single thread called the I/O thread. This is useful to know because this is why a lot of data structures in the network stack don't need to be protected by a lock. And the I/O model is an asynchronous I/O model. So this means you initiate an I/O operation, and we return immediately a status code that says it's in progress. And then when the I/O operation is done, like the read, you say, I want to read. When the data is received, we will invoke your completion callback provided by you on the same I/O thread. So this is the model we're using. And this actually is true for most of the classes in the network stack, except for the top level URL request class. For that class, we have a delegate class that can provide more ways to invoke the callbacks for multiple events. Okay, then the next slide is how the network stack is integrated with Chromium. The network stack, because it needs to access the network, is a privileged operation, so it has to run inside the browser process. The renderer is the one that actually initiates the loading of a resource that starts from WebKit, the web rendering engine. So that load resource request goes through IPC to the browser process. And then there is a class in the browser process called the resource dispatcher host that is responsible for issuing the URL request from the renderer processes to the network stack. So that is a very important entry point into the network stack. But there is another entry point into the network stack called the URL fetcher. And that is used only for URL requests generated by Chromium itself, such as visiting the safe browsing server, or getting navigation suggestions, or sending users' usage statistics to our UMA servers. So at this point, I'm going to turn over to Eric Roman to go into the network stack in more detail.
Hey, so I'm going to talk a little bit about the programming model for how you actually end up issuing network requests and some of the layers that will pass through as you do this. So the main header file you'd want to check if you're going to be programming network requests is a URL request.h. And this describes how to use the URL request object, which is the main entry point into the network stack. So when you construct the URL request, you're going to specify the URL that you want to fetch, as well as a URL request delegate object. And the delegate object is how you receive notification of events during the network fetch. So you specify essentially callbacks for when the response has started, or when the response has completed, when you get a redirect, when authentication is required. And so the URL request object, once you've constructed it, you just call start, and it begins issuing the stuff asynchronously, and your delegate will get called to notify those various events. So the other thing you have to specify at the URL request is the URL request context. And the context is essentially the global state that's shared between network requests. So this includes the cookie store, the HTTP cache, the various network session state, so auth cache, the client socket pool, and a proxy service. And usually the URL request context, you can think of it as one per browser. And so all requests you do will be sharing the same state. So they share the same cookie store, they share the same HTTP cache. The exception is with incognito mode, where you'd actually specify a different URL request context that you can substitute in an in-memory cookie store and an in-memory cache. So I guess we'll just step through a sample request, what happens when you issue, let's say, an HTTPS or HTTP request. So if you have can you hear me? Okay. So if you have the slides, you can follow along on those as well. I'll try and reproduce the similar diagram. Okay, so we're going to start execution in the URL request object. And the arrows here represent dependencies and sort of flow of execution. So we're going to pass in the delegate object, which is how we get called back when events complete. And we also pass in the URL request context, which holds all of our global state. So we're first going to pass into the URL request is going to look at the scheme of the URL. It's going to determine what type of job to create. So since we support FTP, file URLs, HTTP, HTTPS, this is where it determines which specific type of job to use for this request. So in our hypothetical situation, we'll be using an HTTPS request. So what it's going to do is it's going to create a URL request HTTP job. And the URL request HTTP job at this layer, it applies filters, and it's also going to read and write the cookie store. So we'll just write in the cookie master here. And the cookie store comes from the URL request context. That's so after that, we're going to go down to the next layer. This is the HTTP cache transaction, and this is going to enforce the HTTP cache stuff. So it also has a dependency now from more state coming from the URL request context, which is the HTTP cache. So that's also part of URL request context. So if the request can be serviced from cache, it's going to stop at this layer and sort of return that. If not, then it's going to have to actually do a real transaction on the network. So it's going to go down to the next layer, which is the HTTP network transaction. And this is where the real details of the HTTP protocol are implemented. So reading and writing the headers, understanding response codes. Most of that logic is in HTTP network transaction, and it's going to apply authentication, apply the proxy stuff. So at this layer, it's going to rely on quite a bit of state from your request context. Most of this is in HTTP network session. So this is also indirectly part of URL request context is contained in that. And so your HTTP session contains various things. It contains the HTTP cache, the client socket pool, proxy service, a lot of state from here as well. So we'll draw in a couple of those. Okay, and then so now we're near the bottom of the stack, and really the final levels are the socket level things. So if this were an HTTPS request, we'd be talking through the client socket interface, would be talking to SSL client socket. So we'll just write that in here. And so this would essentially wrap a transport socket, which would just be our TCP client socket. And then obviously here we're actually just talking down to the network. So lastly, I was going to talk a little bit about the tests. So if you're going to be working in the network stack and you make modifications, you obviously want to add unit tests. So to run the unit tests, you just use the net unit tests target. And most of the tests use mock dependencies for like at the socket level or mock proxy services, whatever. There are some exceptions. As Wan-Teh mentioned, we also have the test server, and the test server is a Python application where you can create custom responses or handlers for special tests. So that's also an option. So yeah, and there's a bunch of resources you can check out the network stack roadmap, the DNS prefetching document page. There's a documentation on disk cache if you want more information. There's some links in the slides. And I guess lastly, Wan-Teh and I can answer questions. Yes.
So Wan-Teh mentioned reasons for switching away from WinINet and WinHTTP. Can you guys reiterate some of the other reasons besides the 2 GB file download limit on WinHTTP, why we ended up ditching like WinINet, for example?
So the question was to elaborate a bit on why we chose to ditch WinINet and WinHTTP. So he mentioned there were some bugs, in particular, like not being able to do file downloads over 2 GB, and sort of with some other. I think Wan-Teh will.
So with WinINet, we basically run into two major problems. The first one is that we cannot get the certificate, the service certificate, and this is critical when you handle a SSL certificate error. So that one we actually went to extraordinary means, and we were able to get the certificate by patching WinINet. But the other one that we cannot surmount was that it's impossible to tell WinINet to bypass its own cache. And we know that some server generates dynamic content based on the browser's user agent. So we do not want to share the cache with IE. So that's really the reason we had to switch to a new library. For WinHTTP, we could tell that it shares some code with WinINet, but probably because it's not used in IE, the shared code is older, so it has some bugs, security bugs that had already been fixed in IE's version, and we're quite unhappy about that. And it also had some problem that caused system crashes, blue screens on some laptops. So that's another. That one we're also able to find a workaround. But in the end, we just thought that there are too many issues, and it's really, and the porting to Mac and Linux was going to start. So we thought it's time to write our own.
So on Mac and Linux, what's the lay of the land with regard to existing platform network implementations, and whether they're better or worse, the same for us as when
Okay.
HTTP.
So Peter asked about the system networking libraries on Mac and Linux and their quality. On the Mac, I know there's a library called CF Network. I guess it stands for Core Foundation Network. That's used by Safari. So I thought that should be pretty good, but I don't have any personal experience using it. On Linux, the usual problem is not whether there's one. The problem is there are too many, and you need to pick one. So I thought on Linux, we were considering libcurl, or that's quite popular, and there's another one called libneon that's used by the SVN client. I think both would be probably would work well, but in the end, we just thought it's better to just write our own. And the network stack turns out it's not really that complicated, especially the core portion. So basically, Darren Fisher wrote it in within a week, and it was able to do TCP, regular TCP request, HTTP request.
I'm just curious, are we headed in the direction of being able to have our own proxy settings and our own certificate store and not rely on the system for that?
Okay, so the question is, right now we're using the system proxy settings and system certificate store. So the question is whether we're going to support our own proxy settings and a certificate store. I think the answer is, I have two different answers. For a certificate store, I still think it's very important to share the system store with other applications. And we haven't received any complaints about our using the Windows System Store. But with the proxy settings, we do get a lot of complaints from some Firefox users who basically their problem is that they use the same laptop at work and at home, and they have to use their the system proxy settings with IE at work. But for some reason, they want to use, when they use Firefox, they want to use a different set of settings that's appropriate for their home network. And these Firefox users told us that they cannot use Chrome because of this reason. So we're seriously considering adding our own proxy settings.
What are the real-world web compat ramifications of different network stacks, especially rolling our own?
So the question is, what are the real-world ramifications of network stacks, especially we're writing our own?
For website compatibility.
Our experience is that, so the working on network, I think, is similar to layout. On the one hand, you need to implement the standard, but on the other hand, you also need to be somewhat permissive of broken implementations. So our approach has been that we're trying to be as strict as possible. And when we run into incompatibility, we make our best effort to contact the sites to correct it, or sometimes contact, if they're using open source server product, we try to file a bug report. But usually that takes a lot of effort. So we also have to implement workarounds for some of the incompatibilities. Any other questions? Okay, thank you.